You ever look at a massive mountain and just think, wow, that thing is permanent, and an immovable object that's been here forever and will be here forever? Well, what if I told you that's not true? Today, we're going to uncover the secret story of how these absolute giants are relentlessly, piece by piece, broken down into nothing more than dust.
I mean, just look at these incredible rock formations. They feel so ancient, so solid. They look completely indestructible, right? For as long as humans have been around, they've pretty much looked just like this.
But here's the twist. Right now, as we speak, these rocks are in a constant, slow-motion battle. They're being torn apart by simple, everyday forces that you can't even see. This is basically a geological detective story, and we're about to crack the case.
Okay, so let's dive in. To understand how something so massive gets destroyed, first you have to find its weak points, its hidden vulnerabilities.
And believe it or not, the entire process starts right here, not with some huge cataclysmic explosion, but with simple cracks and fractures in the rock. Geologists call them joints, and these are the secret entry points for all the destruction that's to come.
What I love about this is you can see the simple textbook diagram right next to the messy reality. See, these joints aren't just neat little lines. They're this incredibly complex network of fissures that create pathways for nature's forces to get deep, deep inside the rock's core.
And these cracks form in all kinds of ways. Some are just pre-existing, kind of like birthmarks from when the rock first cooled. Others are called expansion joints, and they form when tons and tons of rock and ice that used to sit on top get eroded away. It's a process called unloading, and when that immense pressure is gone, the rock below literally breathes a sigh of relief, expands, and cracks. And then there's my personal favorite, exfoliation joints. This picture shows it perfectly. It literally causes huge, curved sheets of rock to break off and peel away, just like the layers of an onion. I mean, you can see these giant slabs just littered all over the mountainside. It's incredible.
So, now the rock has its weak points. The stage is set. It's time to meet the demolition crew, the natural forces that get into those joints and start doing all the heavy lifting. Two of the main players on this crew are super simple: heating and cooling. Day in and day out, the sun heats the rock, it expands. Night comes, it cools, it contracts, over and over. That cycle weakens it over time. But the real powerhouse? That's frost wedging. Think of it like a tiny, unstoppable crowbar. And of course, you've got other forces too, like plant roots and burrowing animals, which also act as wedges. But frost is one of nature's most widespread and relentless tools.
The whole process is just brutally effective. It's so simple. First, water seeps into one of those joints. Then that water freezes. And when water freezes, it expands by about 9%. That expansion acts like a wedge, just forcing the joint wider. Now imagine that cycle repeating, day after day, winter after winter. You can literally shatter a boulder from the inside out.
And hey, it's not just ice that can do this. In drier climates, you get a similar thing happening with salt. Water with dissolved salts gets into the cracks, then it evaporates, and it leaves those salt crystals behind. As these crystals grow, they exert this incredible pressure, prying the rock apart. We call that mineral wedging.
So the rock is being broken into smaller and smaller pieces. But here's the real kicker. The more you break a rock, the faster it breaks down. It's like a runaway process, a chain reaction. Let's take a look at how that actually works. It sounds a little weird when you say it out loud, doesn't it? I mean, how does fracturing a rock actually make it more vulnerable to the next attack?
And the answer is one of the most fundamental concepts in geology. It is all about dramatically increasing the available surface area.
All right, let's do some quick and easy math here. Imagine you've got a single cube of rock. Let's say its sides are 2 centimeters long. The total surface area on the outside of that cube is 24 square centimeters. Simple enough. Okay, now let's break that one cube into 8 smaller 1 centimeter cubes. We haven't changed the amount of rock at all, right? It's the same volume, but look what happened. The total surface area just doubled to 48 square centimeters. We've suddenly created all this new surface that used to be hidden inside the original block. So here's the crucial point. More surface area means more places for frost, for salt, for temperature changes to get in and do their destructive work. It becomes this feedback loop of destruction. The smaller the pieces get, the faster they break down. Okay, so let's zoom out and see how this all comes together. How do these tiny little cracks and expanding ice crystals end up sculpting the massive, breathtaking landscapes we see all around us?
Well, the key thing to remember is that weathering doesn't happen evenly. It attacks a rock from all sides at once, but it's way more aggressive on the corners and on the edges, simply because there's more surface area exposed there.
And this is the final result, right here in action. Over thousands and thousands of years, this process, which we call spheroidal weathering, just grinds down all those sharp angles. It's what turns a fractured, blocky cliff face into the beautiful, rounded boulders and domes we see in this picture. And it's all because weathering attacks the corners first.
And here's a final thought to really connect all of this. This process, which seems so destructive, this grinding down of entire mountains, it's also an incredibly creative one. It's what produces all the sand, the silt, and the clay that end up forming the soil that all life on land depends on.
So, I'll leave you with this question. If even solid rock mountains are constantly changing, just temporary features on a geological timescale, what does that say about the permanence of the cities, the roads, and the landscapes that we build? Definitely something to think about.